Hi. How's everybody? I see you're already writing in the chat. I'm just trying to select the right binder. So I sent the test, the retest. If you want to take it, you can take it, and then and send it, and then you'll have to review this discussion on your own time. I wanted to start talking about binomial today. That's Unit 5, the beginning of Unit 5. And I said I would take questions, but I guess I shouldn't answer questions on probability because that's, well, and regression. Okay, so I'm not going to talk about the last test, but I want to talk about if you have any other questions, and then we'll get into this unit. Looks like I picked the wrong one. So you can let me know if you have questions. That's the one. Hello. There's only a few people here. I know of about 5 students that said they wanted to rewrite the test, but I thought maybe if I send it, they'll have a better idea of whether they want to write it or not. So any questions, any comments or questions? So I do want to stick with the schedule. And that helps people plan, right? If we stick with the schedule. Okay, so this is Unit 5, so you can pull it out. What we're going to do is elaborate on the binomial distribution. I introduced it in Unit 4, but I didn't get into enough detail whereby you could actually calculate probabilities of certain outcomes. So that's what I want to do right now. Remembering that we call a distribution binomial if the scenario, the experiment, or the phenomenon, the random variable x, has these certain criteria. Okay? So if you're looking at a situation where you are observing and looking for something, you're going to observe and look for something n times, and each time you look, the likelihood of seeing what you're looking for remains the same. It does not change. So what you are looking at are independent trials. Where one of two things can occur, either a success, what you're looking for, or a failure. You know the chance of a success each time you look, and each time you look, the probability P does not change. Okay? The fact is that the number of times you look is fixed. It's known as well. So these are, it seems very straightforward, but there's some details here that are helpful in understanding the binomial distribution. So before I get into this, I'm actually going to give you an exercise. I'm not sure if I posted it on Moodle, on determining whether a scenario is binomial, whether the variable is binomial. Okay, so I'm going to put that up, and then I'm going to give you some time to try it, like maybe 10 or 15 minutes. Okay, so let me find that. Hope it's easy enough to find. Oh, that's not it. Oh yeah, that is it. Okay, just looks different. All right. All right, so here's the problem. So which of these variables defined below has a binomial distribution? Circle the best alternative. Define what a success is in the option you select. Also indicate N and P. All right, so I'll give you 15 minutes to try that, and then we'll get to it. We'll get back to it. Okay, do you have an answer? Which one is it? Which one is a binomial? Only one of those is binomial, believe it or not. So which one do you pick? And tell me the N and P of the one you pick. I'm watching the chat. It's going to mean more if you guys pick one. Have skin in the game. Choose one. Stand by it, and then I'll crush it. If you're wrong. Jasmine says C, the only one who's picking that. Who agrees with Jasmine? Jasmine. Okay, let me go through these. I'll go through each one. Oops. I'll go through each one in turn. So, a 911 operator works one day from 9 a.m. until 5. The probability of a call is known. X is the number of calls received by the operator during her shift. So, looking at this exercise, or looking at this alternative, X is the number of calls received by the operator during her shift. So from there, remember it should be X equals the number of successes in n independent trials. So that means that when you're reading this, X is the number of calls would be the successes by the operator during her shift. Do you see the problem with this statement? What's wrong with this? I mean, it doesn't fit. It doesn't fit with this. X is the number of successes in n independent trials because we don't have an n. It just says, it gives us a time, like a range of time, 9 till 5, but I don't know how many possible calls she could have received, or I don't know what it's out of. Okay? So I don't know the total possible calls she could have received and then how many she received. So I don't know the n. So this is the problem with this one. So you guys can take a screenshot of this or I'm pretty sure this is on the Moodle page, but if you want, I can send it to you. Even though they say P is known, N is unknown. I didn't even need the number. I didn't need to know what P was. I mean, it's known. It means it's known. I'm not going to make calculations. As long as it's known, I could say we have a chance of it being binomial. But the fact that the number of trials is not known makes it non-binomial. So another distribution could be used for that. Often for weighting, that Poisson distribution is used to characterize this distribution, and it gives it a specific pattern given the parameters. All right, next one. An airplane carrying 100 passengers has 2 emergency exits, one at the front of the plane and one at the back. The airplane makes an emergency landing and people exit through the door that's closest to them. X is defined as the number of people who leave the plane from the front exit. So what's wrong with this? I already gave it away that it's wrong. But what's wrong with it? Okay, let's see. Success, failure. People who leave. Well, success is leaving the plane. So that's the success. People who leave the plane, right? So that matches the success. So it's not that. What's wrong with it? Keep going. You're good. That's so you think about success. You think about the parameters N and P. If you cannot identify them, then where P is known and N is independent, then we have a problem. Very good. Yasmin says that the P, depending on the person, right? So we're going to look at our independent trials. Our independent trials, N is 100. We have that. So that's here. N is 100 in here. But the problem is that depending where you're sitting, the chance of getting out the front door is different. So P changes for each person. It's not fixed. It's not known as a set number. All right? All right. Any questions? How about C? So try C. Take a simple random sample of 25 Puerto Ricans, so that's my N. The probability of having a particular blood type is known. Okay, so P is known. I'm going to use a different color for my parameters. So P known. And X is the number of people in the sample with blood type A. So the success is blood type A is the success, and I check 25 people. So P is known, success is understood, and is known. So this is the right answer. Very good. Very good, you guys. All right, so that one's clear. So, you know, start thinking in those terms, like breaking it down into its parameters. You get a feel for this. There's several different kinds of distributions that characterize different phenomena, and this is the binomial. So I'm teaching you, we're focusing on this kind of distribution, but because of limited time, I can't go into others, but you should be able to learn about other distributions, their parameters, and identify them. So I mentioned that this situation, this random variable really would probably be best characterized by a Poisson. This with a changing P would be a interesting distribution, but not a standard one that we have parameters for if that changes, unless you can develop a model of how P changes. The next one is an example of a hypergeometric distribution. So this one, so I mentioned that you would see these other distributions, but I'm not going to spend too much time on it. I mean, I'm not going to spend time. This is about it. That's all I'm going to say about it. Just that you know, there's other distribution that capture these patterns. This one is the hypergeometric. It's not binomial. So let's see, how is it not binomial? You randomly select 5 cards from a standard deck of cards which contain 13 hearts, 13 diamonds, 13 clubs, and 13 spades. X is the number of diamonds selected. So what's wrong with this? Number of diamonds, success is diamonds. So what are P and N? There's 52. There are 52 decks and cards in a deck. If you go through all of them, randomly selecting, and you pick 5, we'll say without replacement. It means that you don't put the card back. So you pick one and you don't put the card back. You pick another, you don't put the card back. You pick a hand of 5 cards. So what's happening is, yes, that's correct, Jasmine, that because you affect the probability of a heart, that's what we're focused on, right? There's 13 hearts. Depending on if your first card was a heart or not, the probability of getting a heart on the next one will change. So that constant changing of probability makes P change. It's not fixed, it's not known. It's random. Okay, so that cannot be binomial. And what about the last one? What's wrong with the last one? So it's good to know what you know and what you don't know. Or it's good in this case to know, by contrast, what's binomial and what's not binomial. So I've given you 4 examples of not binomial. This one also is not binomial. So what's wrong with E? So the problem with E is that you're going to keep tossing. So N isn't fixed. You're going to toss until you get what you're looking for. That's not a binomial. Okay, so it's not set, it's not determined. You can keep tossing until some arbitrary time, until you have a 7 show up on your dice. All right? So with that, let's get back to the notes, unless you have some questions for me. I can say n not known as well, right? It's not known. Okay, let's get back to this. All right, so we have a better idea of the binomial. What is a binomial distribution, what isn't. And now what we want to do is discuss the probability distribution. What are the possible outcomes and what's their likelihood? In fact, here it is. So this is the pattern. Remembering, all I need are the parameters to describe the distribution. So I don't need much more information except knowing it's binomial, knowing the n and the p, and you'll see that the outcomes are always 0 successes all the way up to n successes, because you have n trials. It's a discrete distribution, so there are only n plus 1 possibilities. And here's the pattern for the probability. The pattern, you see, the 0 is here, 0 is here, 1 is here, 1 is here, n is here, n is here. There's a pattern. And I want to describe where that pattern comes from. And then it's going to be easy for you to use and apply this distribution. Now you could, I'm going to show you online, you could go online and find for yourself binomial distribution tables. So before calculators were ubiquitous, or computers, tables, books of tables were created, and people used them. As recent as my education, we were using books of tables. Let's see if I can. So you see how it works here. I can't seem to open one. All right, see if it opens nicely. They always end up blurry. I need to use different software. All right, so this is not bad. So this is a cumulative distribution function for the binomial. The p is on the top. Okay, along the top. Oops. Along the top is p, and down the side, vertically, is your n, and it's showing you if n is 5 in the first case, and p is, well, you get information on all the different p's. It could be, well, there could be more, but these, anything that's not exactly the ones there, you could approximate. And it shows you all the possibilities. Well, n is 5, that means that you could have 0 successes in 5 tries, or 1 success, or 2, or 3, or 4, or 5 successes. I'm not sure why they missed the 5, but these are cumulative tables, so it means that they are adding up as they go along. So let me see if I can get a non-cumulative. Yeah, they always use the cumulative tables. So they always add up at the very bottom of each. It adds to 1, so it ends off with a 1. So I could also do this, in Excel. I could create a binomial distribution. So I could create a binomial distribution. Can you see that? Oh, it's very small, isn't it? There. So I could write bin, and you see there's several of them there. So let's do binomial distribution. Binomial and I put a bracket. Oh, I don't get my hint. Usually it tells me, I'm not used to this version on the iPad. It usually tells me to put the parameters in. Let's see, I'm going to do it on my computer as well. The iPad version is a little bit different, isn't it? I think it's just n and p. If I just put n as 4, comma, p as 0.5, and then if it says cumulative, I will say, I think I have to tell which x I want it to be. 1, I want to say no, not cumulative. Okay, so let me just check on my computer. Okay, no. So I put the number first. So let's say I want if x is 0. So let's do that. So 0, comma, n is 4, and p is 50%, and 0 means not cumulative. There you go. Then I'm going to copy it. But I'm going to change some things in here. So I'm going to change it to 1. So what I'm doing is creating the distribution for n of 4 and p of 50%, which is what we're going to discuss. And the next one, let's see, oops. Oh, why is it not working? Oh, I did it this way. Let's change this to 2. And then three successes and n tries. And the last one is 4. Okay, so that is the binomial for n. So this is x binomial n of 4 and of p of 50% or half. Now if I did this cumulative, what I would do is take the first one and then I just add up this plus the first one. Oops, didn't like that. What did I do wrong? Equals this plus that. Is that wrong? What's wrong with that? Oh, it worked. Okay, then this plus the next one. And then that's what cumulative means. And the last one should always be 1. Okay? So in the code, I've chose, it's 0, because I want the first, the chance of 0 successes. That's the probability of 0 successes. This is the probability of 1 success. This is the probability of 2 successes, and this is the probability of 3, and this is the probability of 4. Okay, can somebody tell me what this is? How do I interpret that result? close, but not as good guess, but the other way around, Hector. Okay, so that is the probability I could say it like that. You can say it in a different way, but that would be the probability of at most one success. To elaborate in 4 trials. Okay, I'll give you another chance. What is this? How do you interpret this one? I should put a column here. Can I put a column there? Insert. So this would be 0, 1, 2, 3, and 4. And that would be little x. Okay, so how do I interpret, what did I say? Oh, this one. So yeah, you could, for this one, you could say at most one success, or the probability of, so another way to say that would be, okay, so what about this one? Yes. So you could call, you could say probability of, you could say less than 4 successes. You could say probability of 3 or less successes. Or probability. So you can see I'm writing this just so you get an idea of how phrasing is done on these questions. Probability of okay, that not all will be successes. Successes. Wow, what a word. Okay. So those all would mean the same thing. So now that we've seen that, let's make the calculations. Now, where do these numbers come from? In this case, there's a pattern and this pattern should be familiar to you because this is for the scenario of flipping 4 coins and recording heads or tails each time, right? And the pattern is symmetric. This value and this value are the same. These ones are the same. In the middle, center value is unique. So where does the formula come from? The formula's in the box here, and I've prepared a formula sheet for the final test and for the final exam that you can use. You can some key formulas are there, and then you can add things onto it. And I will often reference that formula sheet. It's not going to be easy to find if I use this approach. I wonder if I can just go to the end. No, I can't do that in any nice way. So at the end of this Unit 5 and the end of Unit 6 is the formula sheet. And on the formula sheet, you will see this formula as the first formula. Now I want to check, make sure I said that right. I have to go, it's a long chapter. So it's, there it is in the box. Okay. So if x has a binomial distribution with parameters n and p, then x, okay, we'll get into this in a moment, x has a mean np and a standard deviation that looks like that. I'll explain that, and I'll also explain this formula. Notice x is the variable, n and p are the parameters. So I'm going to ask you now, what is k? What does k mean? No, n is the trials. P is the probability of a success on any trial. What's the k? Keeping you guys awake, interested, alert. Thanks for your guesses. Nope, successes is number of successes. Oh yeah, sorry, yes, that's what it is. So what's happening here is x can be 0, 1, 2, 3, all the way up to n, right? So those are all the possible numbers of successes out of n tries. So this is the formula for finding the probability of one of these. So k is just the one of these you're interested in. So I refer to it as the special k, so you realize it's the number of interest. Which one of those are we interested in? So that means that we can only calculate the probability one at a time using this formula. And I'm going to teach you ways around that, because if you have lots of trials, which is more realistic, right? If we want to do this, want to use the binomial in polling, okay? So the binomial is used in polling for elections, for instance, that we've been watching. We saw the results of polling. And I'm not talking about the election polls, I'm talking about polling to see what people might, to predict what people might vote, how they will vote. So the binomial will usually be, employing it, the n could be very large because it represents a sample size. It could be very large to represent a huge population. So that can make what we're trying to do difficult unless we have a pattern. So the pattern, you can see, I'm going to explain where it comes from, and then you're going to have no problem with the pattern from then on out, I hope. Okay, so because this table could be very long. I just showed you the example with 4, but you can imagine that Excel table for binomial could be really long. It could have for 100. And there are tables that people would use with n equals 100 or n equals 1,000. Okay? We don't have to do that, because we're going to use this pattern to help us. Okay, so where's this pattern come from? It comes from probability theory. Remembering this example, so these are the parameters, n of 4 and p of 50%, to describe the number of tails observed in 4 flips of a coin. The possible outcomes are 0, 1, 2, 3, or 4, and this is what they look like. This is the entire sample space. Now, our motivation is that we don't want to have to draw this every time, because for an n of 1,000, that's going to be a lot of paper and a lot of time spent. So instead, we're going to see, there's a pattern here. Let's capture that pattern with a formula. So let's begin down here with just this thing here. Let's see if we can find a formula we can derive a formula in general by beginning with that one event. Now, we already know the probability of that. We figured that out a long time ago. We said that there are 16 possibilities, so this one is 1 in 16. But what we're interested in is what's the probability of 2 successes? So what I'm really interested in is the whole column. So in this case, my K is 2. I already know the answer. I already wrote it up. I know it's 6 out of 16. But I'm going to use the simple example as a model on which to derive a formula that I can use in other cases with larger n and different p's, all right? K is not necessarily the maximum successes, it's just the one I'm trying to calculate at the time. So in this problem right now, I want to calculate x equals 2. So I'm going to begin just with this here. So how would I calculate this probability from first principles? The probability of tail and head, well, from probability theory, these ends just mean multiply, right? We know that because trials are independent, you just multiply these. And I already know the answer. This looks familiar. We saw this in the tables we made before. We saw it in the Excel sheet that I just showed you. Okay, that's 1 out of 16. But I don't care about the answer so much. I want the pattern. So let's look at the pattern. How did I get this? It would be probability of a tail, which is the success, right? That's my success, tail. So that's a P. And the probability of a head, if tail was P, what's head? What's the probability of a head if the probability of a tail is P? Now this works across the board for all binomials because we always make sure there's only 2 possibilities, a success or a failure. That's right, it's 1 minus P. Success, I'm going to do it in black. I'm trying to get a color scheme going. Okay, 1 minus P is the probability of failure. So that's going to be the same for any binomial distribution, so that's as general as I can get. And now, let's put it together. So in a pattern, the probability of a tail and a tail are multiplied, so that's P to the power of 2. And the probability of a head and a head are multiplied, so that's 1 minus P to the power 2. So that's a good pattern, but I need even to be more general. What do the 2's represent in this exercise? How much more general can I get about this? Well, 2 represents the number of successes I'm looking for. That's what K is. And so what symbol would I put on for the number? So this is the number. Let me make this bigger. This is the number of successes. And that leaves 2 failures, right? Or in general, what's the symbol I put here for the number of failures? If K are successes, what would be the symbol for failures? Not P. No. Okay, you guys are close. That's very messy. I'll just call it failures. Idiot got it right, okay? Jasmine, you're close. If there's K successes out of N, then that leaves N minus K failures. Okay? I'll make it again. Got it? So there's N possible successes. The chance of K of them and N minus K, that leaves N minus K failures. How do you check this? Well, add them together. Success and failures should add up to what? Should be the total. Okay? Very good. Till I'm stretching your muscles for you. This is crooked. Okay, so we got that. All we've done now is we've created a formula to derive this. But there's not just one. To figure out N, the probability of 2 successes, I have to do something else. I have to figure out how many will turn up in this column. So the way of doing that is something you should have learned in high school, known as a combination. The symbol for that, so basically we're trying to figure out how would we get 6? What would be a formula for getting 6? What we're looking for is a way to compute the number of successes, or 2 successes in 4 trials. 2 successes in 4 trials. How many ways are there of seeing 2 successes out of 4? This is known as 4 choose 2. 4 choose 2 mathematically is written as have you seen this before? So NCR, or 4 choose 2. Now you don't have to go through all of this calculation with factorials because we're going to use the calculator, all right? So I want to take some time to put this in our calculator together so that you never have to do this. And the people who are not here right now, I hope they watch this video and realize they don't have to do this. I'm going to make this as simple as possible. So let's see. Let's go to the calculator. You have different calculators. That's okay. I'm going to show you how to do it on the BA2 Plus, and you can try it on your own. You can also do it in Excel probably. So let's clear this. What I want to do is go into the data, and there's already numbers there. No, I don't need data. What am I saying? I just want to put 4 choose 2. So I have to look for the symbol. You see it here? I'm flashing it. This is the symbol here above the plus sign. So what I do is I hit 4 second to activate the blue, NCR 2, and then hit equals, and there's the 6. So it's calculated the number of ways I can see 2 successes out of 4. You want to give that a try? Should I do it again? So I really love this unit. It seems ominous, but then once you get the hang of it, it's very easy. I've put the homework for Unit 5 on Moodle. So you have all of the answers. Try not to look at them. Do the homework on your own, and then check the answers. I'm going to do some problems with you before we go today, but I have to admit I feel very exhausted today. I'm going to try and stick with it, stick with you. So solving problems will keep me awake. So I asked you a question. Oh yeah, I asked you to try and punch that in. Do you want me to do that again, or do you know how to do that? Are you good? Did you get it? Let me know that you got the calculation. Okay, do it again. So clear. The button is here. So I'm going to hit NCR. So it's 4 second function NCR 2 equals. One more time. Clear. 4 second function NCR 2 equals. So it's very handy. It's essential for the tougher problems, right? Larger numbers. So that's where 6 comes from. Or you could use factorials to do it. So this is 4 choose 2 is 4 factorial over 2 factorial times 4 minus 2 factorial. If you ever did this and learned combinations in high school, you would have learned this, but I'm not expecting you to know it. So what this means is 4 times 3 times 2 times 1. And this one is just 2 factorial, which just means 2 times 1. So factorial just means consecutively multiply that number. So 4 factorial is equal to 4 times 3 times 2 times 1. They don't put the 1 in because it's redundant. It doesn't change anything. So you don't have to do that because you have the calculator, so don't worry about it. All right, so all we've done is figured out that we got the probability for 1. They should all be the same just because of the way all I'm doing is rearranging. You know, I'm just rearranging these expressions. So the total, the multiple should be the same no matter how I arrange. But there's 6 ways of seeing 2 successes in 4 tries. So that's how I get the thing in front. So that's the formula. So that's the formula. The formula is this. It is successes times failures, and then arrange for k successes out of n trials. That's the formula. And that's just for n, x equals 2. So let's put it all together. Let's punch this in our calculator together. You can always check when you're writing it down, and I'll do some exercises. You can always verify that these exponents sum to n, and these always sum to 1. So it's a good visual tool to make sure you've written things properly and helps you go faster. So this is written properly because 2 and 2 is 4, and these make 1. You see? So what I'm going to do is punch this in my calculator with you from left to right. I do this for the students who struggle with mathematics to make it seamless and easy for them, okay? People who know how to do this, I don't mean to annoy you. I have to address the heterogeneity of the class. That everybody comes with different skill set. And this is a fundamental or introduction course. Okay, so 4 choose 2, and then I keep going. So I'm going to multiply across. Now, depending on the calculator you have, some calculators honor order of operations, so it won't matter how you do it. I think I have to use brackets in my case because it doesn't honor. When I teach the weaker students or struggling students, I usually have them buy the TI-30XA because it does that for you. Oops, it keeps order of operations. Okay, let's go here. So we did the 4 choose 6 already. So 4, second function, NCR2, 4 choose 2, I mean. So that's 6. And then I want to multiply by, put it in the brackets, 0.5 squared bracket times, I think I can just leave no bracket because I'm going to go 0.5 squared. But if I have different exponents, it won't be so easy. And that's my answer, 0.375. Let's go back to Excel and see if we got it right. Yes, we did. That's the one we just did here. Okay? So it was correct. Let's see. That's all we did. We calculated 1 in the whole distribution. We would have to continue with the rest. Let me just check if combinations are here. Probably. I haven't done it in a long time, but probably. Equals combination. See, combine. Let's see if I put it here. Oh, and it tells me how to enter the formula, number and number chosen. So if I put 4, oh, look at that. So that's going to put 4, choose 2, 6. You see? So you have it in Excel as well. Would you like me to do that again? You can just see the formula on the top. Combine, or combination, 4, choose 2. Okay, so there it is. That's the formula we're going to apply. I want to say just a couple more things about, so we just calculated this one. Now I want to look at the other ones for an instant. So to get the rest of them, we would just change k each time. That's it. That's why the formula looks like this. It's the same thing, the same pattern. 0 successes, so that's on the exponent for p. And then if there's 0 successes, then all of them are failures. And then n choose 0. So 0 successes out of n. Then for the next one, it's 1 success So it just changes with the k. So one success, almost all of them are failures except for one, and then n choose one. Okay, so the k just changes all the way around, and you have this general formula. So now you understand it. And I did ask a question about this in another class, probably. I do remember. Although this is symmetric for this case, that these numbers here and here are the same, and here are the same, it's not generally the rule that binomials are symmetric. It doesn't have to be. But it ends up being symmetric when p is 50%. That will be true. And now there's another instance when a binomial will be symmetric, and we'll talk about that when we get through today's class next time. Next class, Thursday night, is a holiday, the 19th. So we're not supposed to have class. But there's probably a day we have to make it up. I need to check the calendar for that. Does anybody know offhand? We have to replace that day. Anyway, I'll email you about it just so I don't interrupt. All right, so if p is equal to 50%, you will see symmetry in the pattern. And then there's another case where you'll see symmetry, and we'll talk about that later. The symmetry comes from allowing, well, in this case, the 50%, it doesn't affect this part of the formula, right? If it doesn't affect this part of the formula, the binomial coefficient does have symmetry. That's what I show you below here. These are the binomial coefficients for n equals 6. And you notice this and this are the same. And this and this are the same, and this are the same, and that's unique. So there's a pattern. So even though I've shown you how to use the calculator, and even though I've shown you that this binomial coefficient comes from this factorial formula, I want now just to appeal to your common sense on how this is calculated, okay? Because I don't want to make you completely dependent on the calculator. That's handicapping you. It's slowing you down when there's some things that, if you understand what you're doing, can speed things up. So it turns out that n choose 0 and n choose n will always be 1. And n choose 1 and n choose n minus 1 will always be n. And that the rest will have this pattern of symmetry. So why will n choose 0 always be 1? Well, what does it mean? It means if you have, so I'll just use the example of 6. So there's 6 outcomes. You could have, let's do this one first. Out of the 6 outcomes, 0 successes. So that means that all of them are failures. How many ways are there of arranging those F's that are unique? How many unique ways are there of arranging the F's? That's the question you're answering with 6 choose 0. There's only one way. Okay, it's just the one I wrote. Got it? And over here, what about this one? Let's try this one. six trials, how many ways are there of seeing 6 successes? That's what this one means. So that would be success, 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 success. So how many ways are there uniquely of arranging the S's? How many different ways can I see those appear as successes? The only possible outcomes are success and failure. So it doesn't matter if I move the S's around, it still looks the same, right? So there's only one way. Okay? Let's try this one over here. So 1 success out of 6 trials. So 6 choose 1, 1 success out of 6 trials. So I'll use color coding. So 1 success and the rest are failures. How many ways are there of seeing that? The answer is 1. Because, 6. What am I saying? Is 6. Because what I can do is just move the S over, right? I can move the S here. And those are unique. And I can keep on going, moving the S, scrolling through. And there'll be 6 different ways. And you guys believe me, I don't have to write it because I ran out of page here. Okay? And similarly, if I just flip the S's for the F's, there's 6 ways to see 5 successes out of 6. So you guys can think about that. So that means the coefficient has a binomial pattern. It's only the inside that makes it, a symmetric pattern. It's only the inside, this multiple here, that would make it not be symmetric. So you can see there's, I can make one up, I can make one up and show you a distribution is not binomial. We can go, not symmetric. I can make one up. Let's see. Let's move this over. I don't know what to do. Let's do another sheet. Let's copy. Let me copy and change it on another sheet. So let's do B is 4 and P is, let's make it 88. And this will affect things. So I'm going to change it. You could probably program this just easily, but of course I didn't do that in advance, but you can see this will not be symmetric. See, it's just a mess. But they do all add up to 1. They should add up to 1 total. Okay, not symmetric. Okay. All right. So now let's solve some problems. You ready? I like to just jump and then I'll go back to this. So you guys can read these notes on your own. It's just repeating what I've been saying. And I say a bunch of stuff here. And we're going to jump to the practice exercises. So then I can leave you with something to work on. So let's try this. And the way you're going to do this is you're going to, for each problem, identify X, N, P, K, just like we did in the first quiz exercise together. If you can identify these as we've defined them for a binomial, then your situation is a binomial. Okay, so try that first one. I'll give you 5 minutes. No, maybe that's too long. 2 minutes. Also, if you can figure out what a success is, that's helpful. Okay, how'd you do? I ended up giving you 5 minutes probably anyways. Did you get anything? Get anywhere? What's x? X can be 0, 1, 2, 3, 4, 5, or 6. Because I'm going to repeatedly roll the die 6 times. So n is 6. I'm going to look for what? What is my special K? Yes, special K like the cereal. What is my special K? So these are my options. But I just want to know a few of them, or one of them. In this case, exactly one. So at this point, there's a lot of numbers floating around that all look the same, 6s and 5s. So you need to clear up what is a success. So when you feel stuck, what is a success for this problem? What's a success? How would you define it? Okay, so yes, you're a little bit confused, but okay, let's clarify. So I'm going to roll the die 6 times. Each time I'm going to look for the number 5. So 5 is the success. That's what is implied by this question. Now, maybe that's not easy at first, but hopefully you get it now. All right? All right, so a success is a 5, and I could be getting no 5s, 1 5, 2 5s, 3 5s, 4 5s, 5 5s, or 6 5s. Now, which one of those am I interested in out of the total number of tries? Exactly 1, you see? So what you want to solve for is a special K of 1. The 5 referred to the thing you're looking for. The 1 is how many of those you're going to get out of 6 trials, okay? And the chance of getting a 5, what is the chance of getting a 5? It's 1 out of 6 because there's 6 possibilities. So you should, if you've never done this before, it could be blowing your mind. There's lots of things floating around here, so we need to tease them apart. You need to, this helps, okay, when you identify what's what. So I have the P as 1/6. That's the chance of getting a 5, and then my special K is 1. So I want to figure out the formula for this situation, and here I'm gonna do it right here. And then you're going to punch it in. I'll do it in blue. And no, I wrote the wrong number. It's x equals 1. So that's equal to, let me erase this so I have room. That's equal to 6, choose 1, 1 6, to 1 success, 5 6, 5 failures. Okay, so this is the P. I basically, I don't want you to be, the formula is there to remind you, but you should be able to do this without looking. This is the P. This is the 1 minus P, and those together should sum to 1. And they do, right? And these as well these exponents should sum to the n, which is 6. So I've done it correctly. And this is the n choose k. Now I've done it with fractions. A lot of people don't like fractions. But to get the right answer to several decimal places, you're going to have to leave it as a fraction. In this unit, in binomial and probability, unit 4 and unit 5 binomial, you need to use 4 decimal places for your final answers, okay? Because we're working with p probability. So that allows for 2 decimal places if you write it as a percentage. So let's see. I'll let you guys punch that in, let you struggle with that, and give me an answer. That's right, Jasmine. So let me see if I'll punch it in too, so we can do this together. And alternatively, you could use the Excel. The Excel you would set up with n of 6 and p of 1/6, and write it as 1 divided by 6, so you keep all the decimal places. And then set it up for the binomial with k equals 1. So you could do that. I can't stop you. Otherwise, if you want to use the calculator, I'll show you on the calculator. So it's going to be 6 choose, and let me clear this, yeah. So 6 second function NCR1, that's the 6, right? I already knew that. I know 6 choose 1 is 6 because I showed you guys that before. And then I want to multiply that by 1/6. I'm going to use 6 and flip the 6 and then put it to 1, but that's going to still be the same number. Did I use a bracket? And then times bracket 5 divided by 6. Yeah, I don't know if I can do this. And then close it. No, that screwed it up. I can't do it like that because I don't have order of operations on my calculator. So I'm going to do it on the side here. I think that's the best thing to do. And simplify first. So we know this one will be 6, right? Because we discussed that. And if you use that rule or use that property, that will help simplify your calculations. So that's going to be 6, and then this is going to be 1/6. This is way better to do just as a fraction. So this is 1/6, and this is 5, 5, and this is 6 5s. And so that's how I would do that. This cancels with this. Oh, then I can just leave it 5/6 to the 5. See, much easier. Simplify it before you punch it in. I'll clean up all this around. So then when you punch that in, 5 divided by 6 to the power of 5. It's 40. But if I kept 4 decimal places, I should get that habit. I told you, right? So 0.4019 would be the answer. Point 0.4019. So the answer is A. Good. So let's see. Let's do a few more, and then we're going to go for the night. And I'm going to leave you to work with this, okay? Work with the homework on this topic. Okay, so let's do this next one. X, N, P, K. Okay, I'll give you a couple minutes. Write down in the chat what those are. I'll do a couple more after this one. There's just a few classic ones I want to do before I leave you to it on your own. All right. So what is X and P and K? What are they? So what's a success? Success would be, I'm looking for feedback. You guys aren't giving me feedback. So success would be heads. Okay? So each time we flip a coin, we're going to flip 4 times, and each time we flip, we look for a head. The chance of seeing a head is always 1/2 or 0.5. And it's possible that we see no heads, 1 head, 2 head, 3 head, or 4 heads. So this should feel familiar because we already did this one. We already set up this variable, this random variable. But the question is regarding no fewer than 2 heads. So what would represent no fewer than 2 heads? No fewer than 2. So that would be all of these. What does it mean? It means that I have to apply the formula for k equals 2, k equals 3, and k equals 4 and add them together. Okay? So that's the catch there. Now, you already have this result, so we could just go to our Excel spreadsheet and pluck out the numbers, but we have to show our work, right? We're going to show how we got these. So, what was the question again? It was no fewer than 2. So from our Excel spreadsheet, we would want to calculate this one, this one, and this one, and we would add them together. So let's calculate them for practice. So we're good at using or applying the formula. And I'm going to do them in unison. So this is the number of, 2 successes out of 4. This is going to be 3 successes out of 4, and this is 4 successes out of 4. And here I'm going to have 2 successes, so it's going to be 0.5, 2, and then 0.52. Because these make 4 and these make 1 in here. And then would be 0.5 now to the 3, and then 1 here, because again, these together must make 4. And then 4 successes, so all of them successes. 4, that means no failures, and then that's it. So we put those in. So what, punch those in or work with those? So 4 choose 2. Let's simplify. Let's simplify. Always better. So we know that one is 6. So, we know some things here. This one is 6. This one will be 4. And this one will be 1. Right? That makes everything easier. Now multiply straight across. Will be easier. So I have a lot of strokes around. Let's see if I can erase this. Okay. So I would just put in 6 times 0.5 to the 4. 4 times 0.5 to the 3 times 0.5. And then just 0.5 to the 4. Maybe I'll do that. I'll do that on the calculator so you can see that. Yes, Jasmine was saying you could also just get these two and subtract from 1 the total of those summed together. So that would be more efficient because you'd only have to punch in the value for 2 of them. So let me show you how you put this in your calculator. I will put in, for people who don't know, so 6 times, I'll use a bracket, 0.5 to the power 4. And there it is, 3750. And for the next one, it's going to be 4 times 0.5 to the power 3 times 0.5. 4 times 0.5 to the power 3 times 0.5, 0.25. Seems a roundabout way, but we're practicing the formula. We need to practice the formula. And that's going to be the last one, 0.5 to the power 4. Okay, any questions? Do you have the hang of this? Are we finished? What you need to do is you need to sum them to find the answer. Okay, these are mutually exclusive results. They're disjoint, so you can just sum them. So yeah, so the answer is C. Okay, what about the next part? Okay. Suppose that 60% of a herd of cattle is infected with a disease. So we define X as the variable representing the number of cattle that are infected. So infected is X. In a sample of size 5, Y denotes the number of cattle not infected. That's the success there. So not infected, if infected is 60%, means 40%, right? With N equals 5. Good. Very good. Okay, so let's try the next one. And these answers are in the notes as well. It's better to see the explanation so you can follow along. So the next test will be binomial and inference. And it should be, like, we're way off our schedule, so it should be in a few weeks. I guess, yeah. Before the final test. Okay, so for this one, let's see if it aligns with the binomial. It's very important that you define your success. Anybody? Okay, let's try this together. A hospital is treating patients who have this fever. 70% of the patients with the disease die, and each patient lives or dies independently of other patients. Okay, so what do we have so far? Sadly, we have 7 patients. So we're going to look and observe 7 for the chance, the sad disappointment that they die. The chance of dying is 70%. Lots of 7s floating around. Okay, so I'm defining this success, unfortunately, is by dying. That's what I'm looking for. I could write it the other way, but this is the most straightforward. So K is what? Well, X could be 0, 1, 2, 3. This is helpful when you list it. 5, 6, 7. The chance that 6 or less die would be all of those. So I'm going to invoke Yasmin's recommendation to do this backwards. We're going to calculate the probability, the special K, for K equals 7, but then take 1 minus 7 to find the probability of all of them. Okay, otherwise you're going to be adding up all those other values and it's a lot of work. Okay, so you can use the complement. So we're really using our probability rules all the time now. So I'm going to set this up. I'm going to write this always together so I don't forget that step. So it'll be 1 minus, and then here I'm going to write out of 7, choose 7, and then the chance is 70% to the power 7, lots of 7s, and then it's a failure rate of 30% chance of failure, but there's going to be no failures. So that's what I want to punch in, and I'll put it in square brackets there. So we're basically figuring out the probability that not everyone dies, that at least one survives. So we know, before we go to our calculator, that this becomes a 1, and this also becomes a 1. So all we have to plug in is 1 minus 0.7 to the 7, unless I made a mistake. Any questions? You guys getting the hang of this? It's all the setup, and then it's just a very it's very repetitive once you set it up. So as I would punch this in, I'll show you how I'll punch this in. I would go 0.7 to the power 7 equals, change the sign and add 1. That's what I would do. Oh, that's not it. What did I do wrong? Hold on. 0.7 to the 7 negative plus 1. That's what I did. Maybe I made a mistake. 0.7 to the power of 7 equals negative plus 1. Now, that's better. So that's 92%. Do it again. 0.7 y to the x is the power button. No, not 5. 7 equals, put a negative in front and add it to 1. So it's 92%. So that's equal to 0.92, or, oh well, I guess I want you to hold all the decimal places, so I will do that. Let's just do that. So hold 4 decimal places, 0.9176. The best answer is this one. One more and then we're gonna go. How's that? One more. Do the next one, number 5. So you need to practice the homework after we do this one. You can finish these notes, read through, and next class I'm going to, well, I gotta look at when we're going to make up that next class, but you can work with the binomial, and then I'm going to get into sampling distribution. So watch the videos available for the SDS, sampling distribution of a statistic. Okay, you can just read the notes and we'll get together. Aha, so here's a problem about SARS. There are 4 patients with SARS in a Toronto hospital who are monitored by 2 staff members. Okay, let me set this up. Maybe it is a binomial. So let's see. So set that up and then tell me what a success is. So what you have to do is read the problem to identify x equals number of successes in n trials. Try and find that part of the expressions in the question. That will help you identify success. Oh, so some of you guys sent me the test, but you're watching the videos too. Very good, very ambitious. All right. All right, so you guys have some suggestions? If I give it to you, it's no fun. You have to try and figure it out. Well, there's 4 patients. And we are going to monitor the patients to see if they need emergency attention. So emergency attention, or needing emergency attention, is the success. Emergency attention. And there's 4 patients, so it could be that none need emergency attention, 1 does, 2 does, 3 does, or 4 does. And the chance, you're told, of needing emergency attention is 30%. So the real question is, for this complete setup, is what is the K? To answer the question. The question is, what is the probability at any one time that there will not be sufficient staff? So which of these options or combination of these options will reflect not having sufficient staff? How much staff? How many staff members are there? Two staff members. And presuming that one staff, I guess that's a hidden assumption here, is only one staff can attend to one patient at a time. So each patient needs one staff member if they need emergency attention. Right. So you have to figure out, if there's only 2 staff members, if 3 or 4 people need attention, you will not be able to have sufficient staff. You will not have sufficient staff. So that's what you have to calculate. The probability that K is 3 or 4. Oops, or 4. So then you calculate them and add them together. And that's that. So I'm going to do that, and then I'm going to go. So special K equals 3, and special K equals 4. And so it's 4, choose 3, 4, choose 4. And the success is 0.3 to 3 successes. And then 0.7 is the leftover for failure to 1, so that these total 1, not 1, 4 or n, and these total 1. Then we do the next one. The chance of a success is 30, and I'm looking for 4 successes, and for failures the chance is 70%, and there's no successes because out of the total, these have to be add to 4 and these add to 1. So there you go. So let's simplify. In simplifying, before we punch it in, this one is 4 and this one is 1. This one is 1. So all you're punching in are 0.3 to the power 3 times 0.7. So 0.3, 4 times 0.3 to the 3 times 0.7. 4 times 0.3 to the 3 times 0.7. So 0.0756. And the next one is just 0.3 to the power 4. So you need to know this button on the calculator, okay? That's the power button. Now you have to sum them. And you get your answer. Did I do something wrong? No, I didn't. 0.0756 plus 0.0081 is B. Okay, so practice that, and I'll be in touch about when we have class. Watch the SDS videos, work ahead with the homework. Okay, even though you have all the answers, doesn't mean you shouldn't do the problems. You should do the problems. Okay, do you guys feel like you learned something? So you know what to look for in a problem? And you understand the formula. Wonderful. Very good. So you guys, there's lots of problems in the homework, okay? So do a nice quantity of them to feel confident. But the one that we just did is probably the most challenging to set it up, to tease apart the parameters and actually the question. Okay, so I'm going to say good night. Unless you have any questions for me that are short, I'm going to wait a bit and say good night to the rest of you. Thank you for sending your tests, the people that did it. The people that did the test and they missed the video or the class, you guys can watch the class later. And let me know if you have any questions.